Hi, welcome back to the video, and in this video I will talk about how to do the numerical differentiation. And before going into the code, I always prefer to know about the concept before coding, because without the concept you don't know how to code. Coding is only a translation between human language to computer language. So if you have the concept as how a human usually solve the problem, you will know how to write the code. So let's start. Normally, to differentiate, we can have three methods to find the differentiation of a function. First is the forward difference, and the second is the central, and the third one is the backward. Why do they have those names? Just go deeper a little bit inside the concept and we will know. So this is the formula to compute the derivative of a function at the x value equal to x1. So if we want to find the first derivative of this red point where the x equal to x1, we need to move one step forward to have the green point. The step size is h. One step forward with the step size h to have the green point, and then from that we can define the first derivative of the f function at x1 using the value of the one step forward point minus our point divided by the step size h. That's why we have the forward difference, because we need to move forward one step size of h in order to have the information to compute our first derivative. And the second method will be the central difference. Why is it central? Because if you want to compute the first derivative at x equal to x1, which is the red point here, then we need to move forward one step with the step size h in order to have the green point. And then we need to move backward one step with the step size also h in order to have the black point. Then we generate the difference between the forward point and the backward point divided by the step size h. We will have the first derivative of the f function at x1, and our x1 is as the central of the forward point and the backward point. That's why we have the central difference. And lastly is the backward difference. For the backward difference, if we want to compute the first derivative of the red point at x equal to x1, we need to move backward one step with the step size of h. We will have the information of the green point, and we need to calculate the difference between our point and the backward point divided by the step size h. Then we got our first derivative at x equal to x1, because the information is gained from the backward point. That's why the method is called backward difference. And I hope that the concept is somehow clear how to compute the differentiate of a function at a specific point. And in our case, I'll use the example at a point where it has the x coordinate equal to x1, and we can find the first derivative of the function at x equal to x1. Lastly, those are the disadvantage and advantage of each method that I already specify here. If you want to read more, you can read it. I just want to specify one thing, is the endpoint. What does it mean, the endpoint? It's the starting point of our function. This is the first endpoint and this is the last endpoint. Every function, finite function, has endpoints. So this is the first endpoint and this is the last endpoint. And okay, let's move forward. How to move from analytical differentiation, as the human usually do, to the computer. How can we compute them numerically? Okay, this is how we're gonna compute them numerically. There are 3 steps. The first step is that we need to generate our x-axis. How can we generate it? We just have to create an array with n numbers of points or values or elements, whatever they are synonyms in this context. So our x-axis are represented by n number of discrete points, x0, x1, x2, and because we have n number, so that's why the endpoint will be x at n minus 1. So it will be a discrete axis, not a continuous axis as humans usually perceive, but discrete point. Each point will define a point, a value of the axis. So this array of n number of x values is our x-axis in the computer. This is our x-axis, and corresponding to each value of the x1 or at the x value along the x-axis, we can compute the function, the value of the function at that point. So the value of this red point here is fx0. Next, the next point at x1, we have the value of fx1, and similarly we will have n points of values or elements, an array containing n number of points of the f function. So this array representing our blue curve, that will be our second step. At the second step, we need to generate our blue curve or our function based on the x-axis that we generated at step 1. And finally, at step 3 is where we compute the derivative of the f function based on the generated array of the f function here. So these are the 3 steps we need in order to convert an analytical differentiation to numerical differentiation. So those are the steps. Let's go into the code. And because I think the video is already long enough, so I want to separate. There are 2 videos. The first video, I just want to explain the concept and also the steps we need to convert from analytical differentiation to numerical differentiation. And in the second video, I will show you the code, explain you the code of one of the methods for differentiation. See you.